In this question, we are going to consider the potential energy as well as the potential at a location P in the following diagram. In order to first determine the amount of work done by an external agent in assembling this array of charges, we have to consider the work it took to put each and every one of those charges in their current place. This is why I'm currently erasing the charges. Let's recall that the potential energy stored in a system of two charges is equal to 1 over 4 pi epsilon 0 times the first charge times the second charge divided by the distance between the two charges. We also refer to 1 over 4 pi epsilon 0 as k, itself being a constant value. I've erased the charges so we can consider bringing them in one at a time. A good question to ask would be, well, why are we calculating the stored potential energy if I want to know the work that was done to assemble these charges? Well, think about it this way. Where did that stored energy come from? It came from the work necessary to arrange the charged particles in such a way that they could then store this exact energy in their configuration. Okay, so consider that we have no charged particles on the screen yet, and we want to bring in Q1. Well, bringing it in will cost us no energy because there is nothing that will either push back against us or pull Q1 towards it. Think about trying to move a planet around in deep space in the presence of no other planets. There's no gravity acting on it. Likewise, here there's no electric field that Q1 has to move through. And so we get to bring in Q1 for free. Okay, now let's bring in Q2. This time, however, Q1 is already there, and so there will be an electric field that Q2 has to move through. The work required to bring in Q2 will therefore be the energy stored between Q1 and Q2 in their final configuration. When we then try to bring in Q3, it will be moving through an E field created by both Q1 and Q2. Therefore, the work required to bring in Q3 will be equivalent to the sum of the energy stored between charges Q1 and Q3 and Q2 and Q3. And so in the end, the total work done by an external agent in assembling this array of charges will simply be the sum of the work done in bringing in charge 2 with the work done in bringing in charge 3. An interesting question would be, does the order matter in which we bring in the charges? And the answer is in fact no. Take a minute to convince yourself by approaching this problem in maybe a different order. Say, bring in Q3 first, and then Q1, and then Q2. Computing the result, we find that it takes negative 4.95 joules of work to assemble the charges in this specific orientation. Let's talk about the significance of the negative sign for a second. What does that mean? It means that the charges were arranged in such a way that overall, an external agent was actually helped by the configuration in assembling the charges. Think about a gravitational field for a second. Imagine lifting a rock from the ground to some height in the air. This would require positive work. However, if we had the rock already at some height and we lowered it closer to the ground, this would take negative work, as the gravitational field would be helping us do this. Likewise, here, the electric field in the end helped us bring in the final negative charge in the presence of two positive charges. Electric potential can be calculated as 1 over 4 pi epsilon 0 Q over R, where Q is any given charge that creates the potential, and R is the distance from that charge to a point in space whose potential we are calculating. The potential at point P due to Q1, Q2, and Q3 is simply the sum of the three. Calculating this, we find that the potential at point P due to our 3-point charges is 15 kilovolts. I want to talk briefly about what potential is. You can think about potential at a location in space being the potential of that location to give a charged particle potential energy. In other words, if only a charged particle were to come along and be placed at point P, there is 15 kilovolts worth of potential to give it potential energy. It is for this reason that sometimes the potential is given in units of joules per coulomb, and also why potential energy is simply a charge times the potential. And so in the third part of the question, already knowing that point P has 15 kilovolts of potential, placing a 4 microcoulomb charge there will give it potential energy. If we then convert all of this stored potential energy in the charge into kinetic motion, we can use 1/2 mv squared to determine what its final velocity will be when it has converted all of that stored potential into kinetic energy. So when the fourth charged particle is placed at point P and it then has 60 millijoules of potential energy stored in it, converting this into motion, it ends up with a final velocity of 8.94 kilometers per second. What we have yet to mention is the wording in part A of the question, where it says that the charges are initially all very far away from each other. The reason why this is necessary is that it allows us to make assumptions about the initial potential energy of each of the individual charges. Being quote-unquote very far away can be considered as infinitely far away in a mathematical sense, and noticing that potential energy and potential both fall off with 1/r, we see that if we are infinitely far away, there is no potential energy due to two charge configuration, and no potential due to a charge configuration, and so this gives us a nice reference that infinitely far away the potential energy is 0, and so too is the potential. So the 15 kilovolt potential at point P was with respect to a 0 potential at some location that is infinitely far away. As always, the full solution is available as a PDF download in the video description below. Thanks for watching!